So we talked about how reactions can be determined by rate of appearance or rate of disappearance, and they can also be determined by the rate of the overall reaction, which is what we use the rate law for. So the rate law is a means of studying how a reaction proceeds over time. So there's actually a lot going on in this equation, several new pieces that we'll talk about. So in this case, it's the rate, which is molarity per second or hour, whatever our time unit is, equal to some kind of proportionality constant, and that's called the rate constant. We represent that with a lowercase k. The rate constant changes with temperature for a particular reaction. Since reactions tend to speed up as you heat them up, if you change the temperature, you change the k. And then we both have the concentrations of A and B, so the disappearance of two products. We always use reactants when we're talking about rate law. And then they're raised to the powers m and n. And this is what we call the reaction order in terms of A and in terms of B. So the order is probably the trickiest part of this unit, figuring those out. But we'll go through and talk about how to pick out the particular reaction order for a particular reactant. Also worth noting at this time, this particular reaction, or this particular equation, is not given to you on the AP sheet. So this is something that you need to know. Okay, so let's talk about those reaction orders. M and N is how they're written on the little sheet right there, or on the equation. They can be either zero order, first order, or second order. That means that values of M or N can be either 0, 1, or 2. These cannot be predicted from looking at a balanced equation. Got that? I'm going to say that again. Reaction orders cannot be predicted from the balanced equation. You got that? One more time. Reaction orders cannot be predicted from the balanced equation. I say that several times because here's what happens. Someone looks at an equation and it says something like 2H2O, and they say, oh, okay, water is second order then because there's a 2 right there. No. One more time. They cannot be predicted from the balanced equation. I reserve the right to mock you mercilessly if you ever do that in class now. They can only be found through experimental data. So in order to determine 0, first, or second, you're going to have to look at data from an experiment, compute the data in order to figure out whether it is 0, first, or second. You do not look at the balanced equation. So experimentally, how this is done is we take a reaction, we do it once with a particular concentration, measure the rate. We do it again with a different concentration, measure the rate. And we'll do that several different times with several different concentrations, and then compare the rate of reaction based upon the different concentrations. So let's say we do one reaction, we get the rate, and then we double the concentration of the reactant and do it again. If there is no effect on the reaction rate, that means that the particular reactant is 0 order. So for example, let's say we do our first experiment and we use the concentration of A as 3 molar. We measure the rate to be 5 molar per second. Okay, then we want to do another experiment in order to determine what the order of A is. And so we would do another reaction, so clean out our beaker, flask, whatever it is, try again, do a completely different reaction, but this time we're going to use 6 molar of A. We measure the rate of reaction and we find out that the rate is equal to 5 molars per second. What that means then is that the doubling the concentration, changing the concentration of A, had 0 effect on the reaction rate. Therefore, it's a 0 order reaction or a 0 order reactant. Now I say doubling, if we were to triple it and use, say, a concentration of 9 molar, it would also have 0 effect on the reaction rate because it's a 0 order reactant. So here's a graph that shows the decomposition of ethanol. So in this case, there's only one reactant, and so that would be like our A that we were talking about in the last slide. And so it's decomposing over time, and we're saying that this is a 0 order reactant, which means the concentration does not affect the rate of reaction. And so what we can see right here then, as concentration is changing, as the concentration is dropping, we get a straight line, which means it has no effect, the concentration has no effect on the rate. Where this is different, if you think back to the last video, when we looked at NO as it disappeared, or NO2 as it disappeared, it started out going really, really fast and then slowed down, so we got that curved line. That curved line tells us that NO2 was not a 0 order reactant. In this case, since over time it produces a straight line, so concentration disappears at the exact same rate, this is a 0 order reactant. So if you're shown a graph like this with a straight line and it's concentration versus time, that means it is a 0 order reactant. Now a first order reactant, if a 0 order reactant concentration has no effect on the rate, for a first order reactant, doubling the concentration would double the reaction rate. So we do a reaction where we use 3 molar of A. The rate turns out to be 5 molars per second. If we do another reaction then, to experiment, clean out our beakers, clean out our flasks, whatever, then we do another one where we use 6 molar, we would find out then, we'd use our stopwatch, oh, what do you know, it was 10 molar per second. So doubling the concentration doubled the reaction rate. And it doesn't have to just be doubling. Let's say if we were to do another one where we got 9 molar, so we tripled the reaction rate from the beginning, what do you know? We would triple the rate. So the rate would probably wind up being about 15 molars per second. So basically whatever you do to the concentration happens to the rate as well. So if you were to half the concentration, well then the rate would cut in half. If you were to triple it, the rate would also triple. If you quadruple, it would also quadruple the rate. So that brings us finally to second order reactions. In this case, if a zero order has no effect, a first order has the same effect, a second order has a doubling effect. So if we double the concentration of a species, it will quadruple the reaction rate. So if the concentration of A goes from 3 to 6 and the rate was 5, it's going to go up to 20. And so what that would do to the rate then is whatever the rate constant is, it would square that concentration. And so it would double the concentration, square it, multiply it by a rate constant, and would give us a quadrupled reaction rate. Now when you do a particular reaction, there's usually more than one reactant, and each individual reactant is going to have its own order. Sometimes they're the same, sometimes they're not. So you'd have to look at data to figure out what the order of A is, what the order of B is, and any other reactants that are in there. To figure out the overall order for a reaction, it's M plus N. So whatever the order for A is plus the order for B. So we can figure out what the rate of a particular reaction is, knowing the concentration of A, its order, the concentration of B, and its order, and then the rate constant for that particular temperature. And the overall order of a reaction can be a third order reaction. You can't have a third order reactant though, it's physically impossible. And so the basic formula for each order of a reaction, so this is the overall order, if the order is 0, then the rate is just going to be equal to K, and that's because it's A raised to the 0, which is 1. The units for K in that case is going to be molars per second. If it's a first order, rate is equal to K raised to the first power for our concentrations, so on and so forth. Alright, so here's a practice problem. Follow along closely because this is what we're going to be seeing a lot of during this unit. So we do 3 experiments. You're going to be looking often at experimental data during this unit because you can't determine the rate order without looking at experimental data. You can't just look at the reaction. So we're going to look at this experimental data and we're going to do 3 things. We're going to determine the rate law, the rate constant at this temperature, and the overall order for the reaction. Now, part A isn't quite as tricky as it sounds. Part A is just the rate law, which is what we were talking about before, where we said the rate is equal to K times the concentration of A, which in this case is going to be NO, and it's going to be raised to some particular power, the order of NO, multiplied by the concentration of our other reactant, which is H2, raised to another power. In order to get the complete rate law, the only numbers we need to plug in are going to be M and N, so we need to figure out what M and N are in order to figure out A. So let's start out by figuring out what M is, so the order of NO. If we look at our experimental data, we see we did 3 separate experiments. So that's 3 experiments where we took our glassware, cleaned it out, did a reaction, cleaned it out, did it again 3 times. Each time we had different concentrations of NO and H2, and we measured the rate of each particular reaction. So if we look at experiment 2 to 1, we see that we kept the concentration of H2 the same. That's good. We can only change one variable at a time. That's scientific method 101. The variable that we changed in experiment 1 and 2 was the concentration of NO. Temperature stayed the same, H2 stayed the same. All the conditions were the same except for nitrous oxide. So in experiment 2, we used 0.1, experiment 1, we used 0.2. So we effectively doubled the concentration of NO. So then we got to look at what happened to the reaction rate. So there's several different ways to figure out the reaction order for a particular reactant, but this one right here is my favorite. It works 99% of the time, and it's actually pretty simple to use. So what it is the first side is rate factor, so that's the factor that the rate changed by. So in this case, it went from 0.0225 to 0.09. And then over here would be the concentration factor raised to the particular order. And so the goal is just to figure out what number goes right there in order to make those two numbers, these two sides, match. So then to figure out the rate factor, we would just take the first rate divided by the second one, so 0.09 and then 0.0225. Hint with this, just put the larger one on top. Always put the larger of the two numbers on top. And then we do the same thing over on the other side. So since 0.9 goes with 0.2, just make sure those are both on the same side. Same thing with the bottom, and raise to an m power. Just to simplify this, then 0.09 divided by 0.025 is 4, and that's 2. 0.2 divided by 0.1 is 2, raised to m power. So in order for these two values, these two sides to be equal, that means m has to equal 2, which means that the reaction is second order with respect to nitrous oxide. So that means if we double the concentration of NO, the reaction rate quadruples. If we were to triple it, it would go up by 12. And so it's a second order with respect to NO. All right, so we're slowly piecing together our rate law. So far we have rate equals the constant times the concentration of NO. We now know that's squared. Now we need to figure out what order H2 is, and we do the exact same thing. So once again, we look at our experimental data. We want to find two experiments where nitrous oxide stayed the same, because we only have one variable that changes. And so if we look at experiment 2 to 3, we would see that nitrous oxide stayed at 0.1, but H2 went from 0.2 to 0.3. And so we can just plug it into this exact same equation that we used before. And so you plug those values in, just the rates over, larger one on top, and then the concentrations. And then if we simplify that, we would see that this rate increased by a factor of 1.5, and it turns out that the concentrations also increased by a factor of 1.5, which means our N value in this case, so the order for our second reactant, has to be a 1 right there, which means it is first order with respect to hydrogen. So that means overall the rate law is going to be rate is equal to the constant times the concentration of NO squared times the concentration of H2 to the first power. So this means we can figure out the rate for this particular reaction based solely upon the concentrations of NO and H2. So if we know what the concentration of nitrous oxide and hydrogen gas are, we can figure out what rate this reaction will proceed at a particular temperature. All right, and the second part wants us to find the rate constant, which is K. So we now know what the rate law is. Now we just need to rearrange it so we can calculate what K is. And so to figure out K, remember K is a constant, which means it stays the same for this reaction as long as temperature stays the same. So that means we're going to need to get a rate for this reaction and then divide it by a concentration squared times the other concentration squared. Where can we get those numbers? Oh, from our experiments. We have 3 choices though. Which one should we pick? It doesn't matter. We can use any of those 3 experiments. We're going to get the exact same K. Why? Because K is a constant, so it stays the same. The only thing you cannot do is pick and choose, like we can't use that concentration and that particular rate. We would have to use all the data from experiment 1 or 2 or 3. So I'm just going to go ahead and use experiment 1. When you are solving rate law problems, it is very important that you write units on everything. Everything, Jeffrey Jones, everything. The reason for that is because the units for K constantly change. It depends on the reaction order. So right here, I've got units written on everything so we can see what cancels out and what doesn't. So what we have as far as units go is molars per second, so that's from the top part, divided by molar squared, so that's that right there, times molar. And so I'm looking at just the units right here. So that means that M is going to cancel out M, and what we are left with is 1 over molar squared times seconds. Okay, so it's 1 over M squared times seconds. That means that's going to be our units on our answer. 1 over molar second times second. Molar squared times seconds. And so now that we've got that out of the way, we can go ahead and plug the numbers in, and our calculator is going to tell us correctly that the rate constant for this reaction is 7.5. And the units on that is 1 over molar squared times seconds. Or another way of writing that would be 7.5 m minus 2 times s minus 1. Other than that, with rate constant, and this is different than other constants, like an equilibrium constant, they have to have units on them. Typically on a question you're going to see on a free response, they're going to give you 1 point for the correct answer, 1 point for the correct units. So being able to write your units in the equation, solve for them, is worth half your points. And finally, the overall order for the reaction. So we know it is second order with respect to the NO, and it was first order with respect to the hydrogen gas, which means the overall reaction order, which is always M plus N, is going to be 3. So it's a third order reaction. Okay, so that's it. This particular type of question, the wording on this and the way you figure out the rate law, then the constant, then the overall order, is very, very common. You're going to see this question a lot. You use data to figure out the order. You find the rate law. The rate law is literally just rate equals K times the particular concentrations raised to their order power. Once you find that out, you find the rate constant. You do that by using any of the experimental data, making sure you put units on everything. After that, overall reaction order. You're occasionally going to see some questions thrown in there too where they're going to say, hey, you've got this concentration and this concentration. What rate's it going to be? In which case you just take your rate constant K that you've already found, plug it in with the orders that you've already found, figure out the new rate.